Hey folks, Nathan here. Today we're showing some updates for the Water Rocket Simulator. We're currently at v0.2 and the simulation has been made slightly more robust and we've actually made it usable. So let's dive right in and see the changes. The first thing you'll notice about our simulator is that we actually have a UI now. So we can enter all our variables really easily, have our units, and yeah, it's a lot more usable than just a tiny little box up here and a bunch of text scrolling down here. But one thing that I really don't like about most rocket simulators that I've found online, at least the water rocket ones, is that the units are typically fixed. So I have to enter things in liters or centimeters or whatever unit the developer of that's decided to go with. And the amount of times I've had to convert from, say, PSI to atmospheres is just a huge pain in the ass, and I'd rather not have to just keep going to Google every time. So what you can do now is you can just click on the unit and it will give you all the options and it will automatically convert things on the back end. So now if you want to have your rocket radius in inches and your tank pressure in PSI, the density in kilograms per liter, you can do all that and the simulator will just put it all in and still spit out the right results. I think that's really helpful. On the right side here, we've also got our important data. So for now, we've just gone for flight time, max height, max speed, and the fuel burnout, or how long after the flight the fuel burns out. You may remember from the first video that we had a whole bunch of text just at the bottom here where we could see every individual time step. So that's still happening in the background, and we're going to be doing stuff with that data in the future, but for now, we're just sort of getting the main key points here just for ease of use. The other main thing that we've changed is just how some of the equations work on the back end to make things a little bit more rigorous. So we know that when you launch a water bottle rocket, the way that thrust works is it's based on the differential between the internal rocket pressure and the external pressure. So the more pressure you have inside compared to the outside, the more thrust you're going to generate and the more lift you're going to get. So the original version of my simulator, and I suspect a couple of simulators online, just have this as a fixed variable. So we put in, all right, this is the external air pressure, and we just run that through the whole simulation. But we know that as we go up in height, our air pressure changes. That's how our barometers work and our altimeters and all that sort of stuff. So this means that we need to, as we go up, figure out what our new height is, figure out what the air pressure should be at that height, and we do that using Bernoulli's principle here. So we need the pressure at sea level, gravity, the molar air mass, current height of our rocket, my starting height, and the universal gas constant and air temperature. So we've added the air temperature variable into the simulator and we've taken out the external air pressure one because we now calculate that on the fly. So every time step we get, based on our height, what the new external air pressure is and use that to calculate how much thrust we should be getting. Because the thrust time of a water rocket is so low, this is only going to add maybe like 0.5% of extra height. So you might get maybe like 5 to 10 extra centimeters in your simulator just because this is in there, which it's not a lot, but I still like having it in there because it just makes it a bit more robust. But the main added benefit that this gives us, which was a nice little side effect, is that we can now feed in what our starting height is above sea level. So because the air pressure at sea level is set at something and then it goes lower and lower the higher we go, if we're launching at sea level, we're not going to get as high of a rocket as if we launch the exact same rocket in the exact same conditions, but 2 kilometers higher, for example. So this means now that you can set your pressure based on what your altitude is above sea level, and you might find that you can get an extra meter or two of height just from that. And that's just with a small 2-liter bottle. If you're doing something large with, say, 4 or 5-liter tanks with a lot higher PSI than what I'm using in the simulator here, we can probably find that you'll get pretty substantial differences in height. So let's jump back in and actually do a simulation. Alright, so we're just going to go with a pretty standard bottle rocket. So we'll go a 5 centimeter radius, a 2-liter tank volume. We're going to go for exactly a third filled. Our fuel density of water is 1 kilogram per liter. Tank pressure, we're going to go with 2.5 atmospheres. The nozzle radius will be 22 millimeters. Drag coefficient of 1, 100 grams of dry mass. The adiabatic index is just a variable that's used for the tank pressure. So for air, that's going to be 1.4. If we're filling our tank with something that's not air, then we're going to want to change that constant. But for now, we're just going to use air, and later on, we'll throw in something that lets you actually change what you're putting into your tank and automatically update that stuff. Alright, let's just say we're starting right on sea level. Gravity constant of 9.8. Air density is at sea level 1.225 kilograms per cubic meter. And we're going to go with 20 degrees of air temperature. So the important thing with this simulation is the time step. If you have something that's too large, where if we say 100 milliseconds, run it. It has to be larger than 0. Make you 1. We simulate it, we can see that we get a pretty dodgy result here, just because in that 100 milliseconds, way too much has happened, so it just sort of breaks the simulation. So we can go down to say 10, simulate that, get a max height of 8.5 meters, go down to 1, this is sort of where we start getting accurate results in the simulator, so this is 1,000 time steps every second. And if you want to go all out, we can go down to say 0.01 milliseconds, which is 100,000 time steps per second, simulate that, and we're starting to get some more accurate results here. This is about as fine as you get. If we go to say 1,000,000 time steps per second and simulate it, takes a bit, and yeah, we gain 0.01 seconds and 0.01 meters per second of speed. So 100,000 steps per second is a pretty solid amount, and the simulator runs really quick. So we can see here with the starting level, if we're at a place that's say 1.5 kilometers above sea level, and simulate it, we go from 16.2 meters to 17.58 meters. So just by launching one rocket from right on sea level to going up 1.5 kilometers, we've gained an extra meter and a bit in height. While this is good, there are still a couple of issues with the simulator that need to be sorted out, mainly just in the math side of it. So things like having a fuel volume that's larger than your tank volume is considered valid, and that shouldn't be, obviously. And it looks like there's a couple of math issues around higher pressures, but they should be relatively easy to iron out. So I reckon the V0.3 will take that into account perfectly. And that's the simulator thus far. So it's definitely a bit more convenient now than some of the other ones that are out there, but we'll need actual flight data to test it out. The next video I put up should be a Hydron video with an FC1 flight computer, as we still haven't had proper success with that flight computer, mainly due to mechanical issues, whether it's the parachute cords not coming out or the Aquarion tank breaking on the launch pad, which still hasn't been fixed. So hopefully we'll be able to use that flight to test out the accuracy of our simulator and make sure that the FC1 actually works. But that's all for this one. Catch you later.